This presentation is entitled Graph Navigation in a Relational Database Management System. Now today, most structured data is stored in the form of a relational database management system. One of the problems though with current relational database technology is it doesn't do well with regard to graph navigation. It's easy to represent graph structures using relational technology. It's not so easy to do navigation on a graph structure using relational technology. As a result, other technologies have cropped up today, such as graph databases. What is presented here is a way of utilizing some exciting new technology that in fact solves the limitations of relational technology that we see today.
Graph navigation in a relational database management system. There are a number of challenges in information technology. In today's presentation, we're going to talk about two of them. Something called queryability, the inability to easily navigate complex structures. The second being one of the notion of fragility. Oftentimes in an enterprise system, whenever you make a change to one layer of the architecture, you get this ripple effect where you break other layers. So we're going to talk about a solution to these two problems. To address the problems I identified on the last slide, we're going to look at a technology called TCSQL. In particular, we're going to look at some graph capabilities, namely the ability to maintain transitive closure. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. Given the graph, one of the things you can do with relational database technology is to represent the components of a graph using relational database tables. So in our graph here, we can represent the nodes of this particular graph with a node table. We can represent the connections of this graph using a connection table consisting of parent-child pairs. One of the classical things you want to do with a graph is the ability to navigate the graph. So, for example, let's assume in this graph we would like to know all of the descendants of this graph starting from node N1. There are three classic approaches to navigating graphs using relational database technology. The first is what I'll call a brute force approach. A second approach uses something called recursion. And the third approach uses something called transitive closure. Relational database technology uses something called SQL. SQL is an industry standard relational database language. Relational database technology uses the notion of tables, which have rows and named columns as the primary data storage. SQL is a declarative language. It provides various constructs for inserting, updating, and deleting records in these tables and the ability to query on these tables. SQL has a strong mathematical foundation built on something called relational algebra. Let's use SQL to explore a brute force method for navigating a graph. So given our graph here that we see, we would like to find all of the descendants of this graph starting from node N1. The brute force method looks like the following. We have these select statements here, union select statements, representing the various levels of the graph. So one of the problems with this approach is you have to have hard-coded knowledge as to the number of levels of the graph in advance. Let's look at a recursive approach to navigating a graph. So given our graph here, use of recursion looks like the following. Given a graph here in the starting node N1, in a recursive approach, what happens is the following. You have a function that returns the immediate children from your starting node. So in this example here, your starting node is N1, it returns the children N2, N3. What happens then is that function is called again with new starting nodes. So that function is recursively called over and over again. The SQL for that would look sort of like the following here. Now, one of the problems with recursion is it's very, very slow. You have to navigate all of the nodes in the graph to do navigation. And so this can be very, very slow if your graph is very large. The third navigational approach we're going to consider is with the use of something called transitive closure. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with N1 and looking at N6. Does there exist a path, directed path from N1 to N6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from N2 to N6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So N2, N6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of N1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal N1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of N1. We see that in green here. And let's find all of the children from all those records. And what we find is we get N2, N3, N4, and 5, N6. So in fact, that represents all of the descendants of N1 here. Now, one of the unique things about transitive closure with respect to TCSQL, TCSQL features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. One of the features of TCSQL is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. Let's talk about a real live use of transitive closure. A number of years ago, I worked for a telecommunications company in an organization whose job it was to track telecommunication switching system projects. It turns out back then the use of tools like Microsoft Project were not an option because the projects were so complex, entailing potentially tens of thousands of underlying tasks. So your classic task network process didn't work very well. You ended up creating PERT charts that made great wallpaper but were too complex to manage projects. So instead we built our own system. We built it off the notion of a work breakdown structure. So we had the notion of projects broken down into features broken down into software and hardware chunks, software broken down into design units broken down into code units. So we had a template here, and for each kind of entity here, we had one or more relational database tables associated with it. So this was our first crack at developing our own system here. It did not use transitive closure initially. So one of the big parts of our tracking system was our reporting system. So given our template here, you would see an instance of a project that may look like the following. Here's a couple projects. So we have project P2 broken down in features, broken down into software and hardware units, so on and so forth. A classic kind of report you'd want to generate is the following. Given a particular project, tell me all of the stuff, in other words, all of the descendants of this project that comprise the project here. So what we would have to do for such a report is write a query that looked like the following here. For every kind of entity in here, what you'd notice is you'd have a select statement pulling data from the associated tables associated with that entity here. Now it turns out in the diagram here we show 6 different kinds of entities. The real system had more like 50 different kinds of entities. So the query in fact wasn't simply these 6 union select statements, it was in fact about 10 times longer here. And the truth of the matter is such queries didn't actually run, they were too complicated. So instead we had to break down reports of this nature into smaller chunks, smaller select statements, and then glue the intermediate results together using procedural code. Now notice here what happens if I were to change my template here. If we were to take hardware and tomorrow we decide to break this down into smaller chunks of work, what happens to reports of this nature? Well, they break because we've hard-coded the knowledge of the structure of my template here. It turns out project managers using our tracking system typically were making process changes on a daily basis. So they were constantly modifying this template here. So what was happening is our set of reports were literally breaking every single day. So what we ended up doing is replacing our system with a system driven from the notion of transitive closure, treating this as a graph problem. So the long queries that you saw on the previous slide could be replaced with a single select statement here. And so notice here that in this select statement, we're not hard coding the structure of our template here. So if the structure of our template changes, if we add or delete nodes or connections from our template here, our queries, our reports are always correct. We've solved what's known as the fragility problem. So why is this valuable? We've demonstrated the solution to 2 major problems. First of all, we demonstrated the ability to navigate very complex structures using this notion of transitive closure. Secondly, we demonstrated that by modeling a problem as a graph problem, the use of transitive closure enables you to write queries such that as you change your underlying model of your problem, the queries are written in such a way that they never break.